When doing a test of independence, or we call these sometimes a test of association, the null hypothesis is that the two variables or factors that we're considering are independent of one another, and the alternative is that there's some dependency between them. So in the example that is embedded throughout section 7.2, we're looking at traffic cameras and injuries. So they've been putting traffic cameras at high-risk street intersections to reduce the severity of accidents, and some citizens' rights groups have complained about the effectiveness of these cameras, and they doubt that they actually have an impact. So we have a sample of 2,938 accidents, and then the type of accident. So this is a categorical variable. So was it a death or disabling injury, an evident injury, or a probable injury? And then we also have whether or not there was a camera at the intersection. And so what we want to know is if there is a relationship between severity of the accident and presence of a traffic camera. So our null hypothesis here, which I've already written out, would be that the accident severity and the presence of a traffic camera are independent, or you can also say not related or not associated. Those all mean the same thing. The alternative then is that accident severity does depend on the presence of a traffic camera. And so we're trying to investigate whether or not there is a relationship between these two categorical variables or there isn't. So what we need to do, like we did in 7.1, is we need to find out what would we expect to have as our counts if the null is true. So if we really have independence between our two categorical variables, how many would we expect to fall in the various categories? So here's our actual data table. And so you can see we have the three severities, so 3 rows. We have 2 columns, whether or not there's a camera there. And what you'll need to do if you do not have totals already is total them up. So I've added all the totals on the sides. And if we add up either the 3 row totals or the 2 column totals, we see we have 2,938. So using something we know about probability, which is if we have independence and we want the probability of A and B, we can get that by taking the probability of A times the probability of B. That's actually what guides us to find our expected counts if the null is true. So we're asked first to just find one expected count, which is what's the probability that an accident was categorized as death, disabling, and before cameras? So using our probability statement, the probability of this death, disabling part and before camera, we know if the null is true and we have independence, this is a probability of the death, disabling category times the probability of before. And so what would this be? The probability of death, disabling, we have 88 in our table out of 2,938 that fall in there. Probability of before is we have 1930 out of 2,938 that are before. Now this is a probability and we really want to count. So then it asks us how many. So when we're asked the question of how many would fall in that category, we would take our total of 2,938 and we'll multiply by this 88 over 2,938 times 1930 over 2,938. And that will give us our count of 57.808. What we do see that's actually more important is if we cancel out a couple of these, what we're left with is 88 times 1930, which is this row total and this column total being multiplied, and then we're dividing by the overall total. So this simplifies down to this, row total times column total over n. And so that's how we can find all of our expected counts. So I'll walk through a couple more of them from our table. So we've done this death disabling before. If we want to do this one next, we have a row total of still 88, but our column total is 1,008. So we multiply those, divide by 2938, and we get for that one 30.192. So that would be the E for that next one. If I move down here to evident, I have a row total of 346, column total of 1930, divide by 2,938, and I end up with 227.291. Then if we move to this one, we would take the 346 times the 1,008 and divide by 2,938, and so on. So we have this first one, this is the second one, this is the third one. I'll jot down the other ones. 1644.901. And then we have, this next one was actually 118.709, then that one, and then finally 859.099. So those are all obtained by taking the row total times the column total over the overall total of 2,938. Okay, what we want to do then is compare what actually happened in our study, these are the O's, to what the null says should happen, these are the E's, through the same test statistic form that we saw in the last section. So we look at O minus E squared divided by E. So to save some time, I've already written out what that looks like for this problem. So we have in this part here, all the O's from our table are these first counts. And then all these other numbers are the E's, which was row total times column total over N. If you add them all up, we'll get a total for our test statistic of 4.7. Conditions are still that all E's are greater than or equal to 5, and that checks out here, so our sample is big enough. And then our degrees of freedom for these problems is number of rows minus 1 times number of columns minus 1. We had 3 rows because we had 3 accident categories, and then we had before or after camera, so we have 2 columns. So this is 2 times 1, so we get a degrees of freedom of 2. So we go to the chi-square in StatKey, degrees of freedom 2, and look in the right tail. And then we enter our test statistic, which was 4.7. And we get a p-value of 0.095. This is greater than our 5% significance level, so our conclusion here would be to fail to reject the null. And in failing to reject the null, we do not have evidence of the alternative. So we do not have significant evidence that accident severity is associated with having traffic cameras.